An unusual object is currently moving through our solar system, and astronomers are paying close attention as new observations continue to reveal unexpected details. Unlike many distant cosmic events that remain theoretical or hard to observe, this one can be tracked in real time as it travels through the inner regions of the solar system. The object, known as 3I Atlas, originated from outside our solar system and entered on an interstellar path. At first, it appeared to be another visitor passing briefly through our cosmic neighborhood before continuing its journey into deep space. But ongoing observations have shown characteristics that make it more complex than initially expected. As the object moved closer to the Sun, researchers noticed that its brightness did not rise in the smooth and predictable way commonly seen in many icy bodies. Instead, subtle changes appeared repeatedly, suggesting that certain regions on its surface may be becoming active at regular intervals. Spectroscopic observations also detected a faint green glow linked to carbon-based molecules. While this type of signature is not unusual in cometary objects, the distribution of the emission appeared uneven rather than forming a simple and balanced cloud around the object. Certain areas seemed brighter at different times, creating a shifting pattern. Its tail structure has also attracted attention. Some observations suggested faint extensions that did not fully align with expected directions influenced by solar radiation and solar wind. Similar effects can occur naturally due to viewing angles, dust behavior, or rotational motion, but the repeated appearance across different observations encouraged further study. Chemical analysis revealed the presence of compounds such as methanol and hydrogen cyanide, molecules often associated with early chemical building blocks found in space. However, one surprising detail was the relatively weak water signature compared to what is commonly observed in many active comets. This difference may indicate that the object formed in a distinct environment beyond our solar system or that its outer surface hides deeper material beneath it. Scientists are still exploring these possibilities. The object's movement also shows small deviations from purely gravitational motion. Such effects are often caused by outgassing, where gases escaping from the surface create tiny thrust forces. Yet the observed pattern appears more organized than expected from random activity alone. Researchers are testing models involving irregular terrain, hidden cavities, and delayed heating effects, but no single explanation currently accounts for every observation. Its orbital path adds another interesting element. The trajectory passes through regions associated with several planetary orbits, including those near Venus, Earth, and Mars. Although such alignments are uncommon, they remain possible for interstellar visitors entering the solar system. Another detail drawing interest is its relatively close alignment with the ecliptic plane, the broad region where most planets orbit the Sun. Whether this alignment is coincidence or the result of earlier gravitational influences remains uncertain. Brightness measurements continue to show repeating variations occurring over intervals of several hours. These changes could reflect rotating active regions, uneven surface composition, or different materials responding to solar heating at varying rates. Light scattering studies suggest the dust surrounding the object may be more uniform than what is typically expected in many cometary bodies. This could be linked to long exposure during interstellar travel, radiation processing, or unusual grain characteristics. There are also occasional hints that additional material may exist around the object, possibly fragments or loosely connected debris. However, these detections are inconsistent and may also result from observation conditions or instrument sensitivity. Future gravitational interactions, especially with larger planets such as Jupiter, may influence its eventual path as it exits the solar system. Even small changes can alter the direction of an interstellar object over long distances. Despite these unusual characteristics, scientists remain cautious. Every observed feature still has at least one natural explanation. The difficulty is that multiple possibilities exist simultaneously, and none yet provide a complete picture. Objects like this are valuable because they carry information from regions beyond our solar system. They preserve chemical and physical records from environments humanity has never directly explored. Whether its unusual behavior comes from interstellar chemistry, long-term exposure to space, or simply the diversity of small cosmic bodies, 3I Atlas is already helping refine our understanding of how objects behave across interstellar distances. For now, it remains an object that is neither fully understood nor truly mysterious. It sits in the space between known science and ongoing discovery, reminding us that even within a familiar solar system, new arrivals can still reveal something unexpected. As observations continue, researchers are focusing not only on what 3I Atlas is doing now, but also on what its internal structure might reveal. One possibility being explored is that the object is not a single uniform body at all. Instead, it may contain layers formed under very different conditions over long periods of time. Interstellar space is not empty. Over millions or even billions of years, objects traveling through it are exposed to radiation, particle impacts, and extreme temperature cycles. These processes can slowly alter outer surfaces, creating hardened layers while preserving older material beneath. If this has happened to 3I Atlas, the activity seen today may represent fresh regions becoming exposed as sunlight heats the object. Thermal models suggest that some volatile materials could remain trapped below the surface until enough energy penetrates deeper layers. Rather than producing continuous activity, this would create delayed outbursts or repeating activation patterns as hidden pockets release gas over time. Another question concerns rotation. Periodic brightness changes imply that the object may be spinning with enough regularity to expose different regions repeatedly. If certain areas contain more volatile material than others, each rotation could trigger temporary increases in activity. This idea fits several observations, but not perfectly. Some brightness variations appear more stable than expected from highly irregular terrain, leading researchers to investigate whether the object's shape itself may influence the pattern. High-resolution imaging attempts are also searching for clues about surface geometry. Elongated structures, uneven mass distribution, or fragmented components could all affect both brightness and outgassing behavior. Meanwhile, chemical studies continue to expand. Every spectrum collected adds another piece to the puzzle. Small differences in molecular abundance can reveal where an object formed, what temperatures it experienced, and how long it may have traveled before entering our solar system. Because interstellar objects are extremely rare, opportunities like this are limited. Most known small bodies originate within the solar system itself. But visitors such as 3I Atlas bring material shaped in entirely different stellar environments. This makes every observation valuable. Even details that appear unusual today may eventually become part of a broader pattern once more interstellar objects are discovered in the future. For now, astronomers continue tracking its motion, refining measurements, and comparing models against incoming data. Each new observation narrows possibilities, but the complete picture remains unfinished. And that uncertainty may be the most important part. Scientific progress often begins